Hi, this video is an introduction to the concept of concavity and how it relates to the second derivative. First, let's define concavity. Before I begin with the definition of concavity here, I would like you guys to recall the definitions of increasing and decreasing on a function. Let's say we have some function f of x. If we know that the derivative f prime of x is positive or greater than 0, the conclusion is that f of x itself is increasing. That's the same thing as saying when the function is going up, the slope of the tangent line is positive. Likewise, if the derivative of f of x is less than 0 or negative, then the function itself is decreasing, and that's because when a function is going down, the slope of the tangent line is negative. Okay? So what's the definition of concavity? Concavity actually speaks to whether the rate of change of the function is increasing or decreasing. So first we'll go over the type concave up, and then the other type's called concave down. Okay? If the rate of change of the function is increasing, then f of x is known as concave up. Now take a look at the difference between this statement here and this statement up here. This statement up here for review is the fact that if the first derivative is greater than 0, the function itself is increasing. However, down here I'm not saying if f is increasing, I'm saying the definition of concave up is that if the rate of change of f, or the derivative f prime, is increasing, then the original function f of x is known as concave up. Likewise, we can define the other one, concave down, by saying if the rate of change of f of x is decreasing, then the original function f prime is concave down. Okay, so let's put these sentences together with what we already know about the words increasing and decreasing that you see here, and then we can see how this relates to the second derivative, which is the derivative of the derivative. Okay, that's what I've got written over here. So the rate of change of f of x is known as the derivative f prime. That's the instantaneous rate of change, all right? Now this sentence over here says the rate of change of f is increasing, and you see over here I've written that as f prime of x, the rate of change of f is increasing. That's when we call f concave up, okay? So the rate of change is increasing. Over here we say that if something is increasing, its derivative is positive. So what I've followed through over here with is that the rate of change, when we take the derivative of that is what is to be positive if we're going to say the rate of change is increasing. You see? Because if a function's increasing, its rate of change is greater than 0. So if the function that I'm talking about happens to be the rate of change f prime, if that is increasing, then its derivative, the derivative of the derivative, is positive or greater than 0. Okay, so what happens when you take the derivative of the derivative? You see I've got the f prime inside here, and then I'm going to prime it again. That's also known as f double prime, and that's what we call the second derivative. Now if you're worried if this is going to be hard to do, it's actually no harder than taking any of the derivatives you've taken before. In order to get the second derivative, first you take the original function f, then you take its derivative and you get the equation form of that. And then you just take the derivative of that, just like you did the first time, and then you will arrive at the second derivative. So you already actually know how to get it, but you've never probably thought about getting it before. The second derivative is the rate of change of the rate of change. Interesting. Okay, so we'll go into some pictures and interpretations next, but just to finish this off, likewise, if the derivative, the rate of change of f, is decreasing, that is to say, that's the definition of concave down, then what happens is the derivative of that derivative, also known as the second derivative, or f double prime, is negative. The overall conclusion about concavity and the second derivative is that if the second derivative of a function is positive or greater than 0, you will call the original function f concave up. If the second derivative is less than 0 or negative, then the original function f is concave down. Alright, so that's enough of all of this. You might want to copy this down. And let's get to the picture part of it. Okay, so the most classic analogy that people use for concavity is that of a car, because most of us are kind of used to what it's like to drive in a car. So let's pretend that the original function in question is going to be the position of our car, let's say on a straight line road, okay? So let's call f of x the position of a car at the time equal to the value x. All right, so let's say I was going to take a graph. Here's x, and maybe that's in time, like in hours, let's say. And here's f of x, and that's going to be my position. Maybe we'll put f of x in miles, and maybe x here, we'll put it in hours. All right, and this is going to get you to the familiar place where first I'm going to draw the position of my car. But now I'm going to consider what does the derivative of this represent. Okay, so first let's do a little more review. If my f of x is in miles and my x is in hours, what are the units on f prime? Remember I told you each and every time the units on the derivative are equal to the y units divided by the x units. So write down not exactly what this equals because I didn't give you an equation, but f prime of x is in the units of what? The y units over the x units, so miles per hour. Okay, so the derivative f prime of x is in miles per hour. Okay, and then maybe that sounds familiar, see why we're using the car analogy. So what do you think the f prime represents? That's right, it represents the velocity or the speed of your car, which is how fast you're going in your car. Okay, so f of prime of x is in miles per hour, and f prime of x is the speed. Or usually, if there's any physics buffs out there, this is actually the velocity, which has a directional component to it. But for now, for simplicity, we'll just say the derivative is the speed. Okay, which is to say that if I've plotted your position on the road, you see I'm getting farther and farther along on the road, and then I take my instantaneous rate of change, conceptually the slope of a tangent line right here. Whatever the slope of this green line is right here would be exactly the readout on my speedometer in miles per hour at this point in hours. Okay, so the slope on this line, the m, is in miles per hour. Okay, now my question is, what is the sign of f prime for the function that I've drawn here? You can see that the function's always going up, the position's always going up, so what would we expect out of f prime? F prime of x is always what? Positive, that's right, it's always positive because my function's increasing the whole time, so f prime of x is always positive, or as we called it over there, greater than 0. Okay, so that's what the derivative of that function means in this analogy. But now let's consider what the graph of the derivative would look like, and then what is the derivative of that? What is that supposed to mean? All right? So we know that this derivative is always positive, and let's just pretend a little farther, and let's say not only do I have a graph of f of x, but along the same axis, so x is still in hours, I'm going to plot as well f prime of x, and you can see that f prime of x compared to f of x, that's going to be in miles per hour. Okay, so what I want to do here is I have the position function here, and then I'm going to draw the velocity or speed function right below it right here, and you can see that maybe not only is the car increasing in its position on the road, but it's doing that at an increasing rate. Okay, you see how this car is not only going farther and farther along, but it seems like it's curving up faster and faster? Well, that's to say that if I consider the slope of the tangent line at different points along this curve, first that green slope would be kind of shallow, right? And then as I move my hand farther and farther along, you see how the tangent line is getting steeper and steeper as I go along? So what I'm plotting over here is I'm plotting the value of the slope of the tangent line to the original function, okay? And that's not constant. This car is not driving at a constant speed. The speed of this car seems to be increasing in time, which is why the position of it is curving upwards in that manner. This is what we're going to call concave up. If you see over here, the definition of concave up is that the derivative, in our analogy of the speed, is increasing as a function of time. You can see that first, maybe I was going like 3 miles per hour, then 6 miles per hour, then 9, and I'm going faster and faster still. My speed is increasing over time, okay? So, do you think that this original function is concave up or concave down? It's concave up, right? Because concave up means that the derivative of the function is increasing, okay? So now we look at this function right here, and we notice that f prime as a function is increasing. Okay, now we're going to start thinking about the second derivative. The second derivative is the derivative of the derivative, okay? Let's see. That's going to represent the slope of the tangent line to this function right here. Do you think the slope of the tangent line to this function is positive or negative? Well, it's got to be positive, right? Because f prime is increasing, okay? Which is to say that f double prime is greater than 0. All right, now I don't know if f double prime itself is increasing or decreasing or whatever, but all I'm saying is that the second derivative is positive because I can see that this function is going up, and so the slope of the tangent line to this function is a number that's greater than 0. All right, does that make sense? What does f double prime represent? If f represents the position of the car, f prime is in miles per hour, that represents the speed of the car. What does f double prime represent? F double prime is in... You know, every time I try to think about what the derivative represents, it brings me back to the question of what are the units on that thing? If I knew what the units were, that would kind of help me to understand exactly what it's trying to describe. Just like over here, the units are miles per hour, so that's how many miles you would go inside of an hour, right? Alright, let's practice our units again. If I took the derivative of the derivative to get the second derivative, the units of this would always be the y units over the x units. Except the y units here are going to be the y units on the first derivative. Okay? So now try to form for me what I'm going to write down as the units on f double prime. It's the y unit of f prime divided by the x unit, which hasn't changed at all. X is still in hours. So that's going to be in miles per hour, or miles per hour squared. Miles per hour squared, if you're a physics buff, maybe you're more used to meters per second squared. These are the familiar units of acceleration, right? Okay, so maybe you're more into cars than you're into physics. You know what acceleration is, right? As soon as that light turns from red to green, you hit on the gas, and then your car, not only does your position increase, but your car's speed is increasing, right? So first you're going 0 miles per hour, you're waiting for that light to change to green. As soon as it hit green, your foot goes on the gas, and you go from 0 miles per hour to 5 miles per hour, to 10 miles per hour, up to 20, 30, 40, and depending where you are, what type of road you are going to accelerate into the appropriate velocity. Okay? So the second derivative is actually the acceleration, and its units are going to be miles per hour squared. When acceleration is positive, then our original function is concave up. That's because when the second derivative is positive, the original function is concave up. Alright, if the second derivative was negative, then the original function would be concave down. Now I'm telling you here in this analogy that the second derivative is analogous to acceleration. So if my second derivative is positive, that means my car is going faster and faster still. It's accelerating. What about if the second derivative is negative or less than 0? What would that look like? Let's try to picture that. Okay, so I'm going to want you guys to try to picture that, and so we can kind of see something that's concave down. I want to consider a position function of a car where, let's say I started right here on the road, and I'm going to be going slower and slower and slower still. Okay, I'm going to be decelerating. What do you think that looks like? Actually, I'll start it over here, just like I did before. Okay? Did you draw something like that? Let's analyze this and see how this interprets as concave down. Okay, now the first thing I want you to notice about this function is that this original function here, f, this is still in miles. This is f in miles. And then the x here is in hours. Is the function I drew here increasing or is it decreasing? It's still increasing, right? Now, remember the thing that I drew before kind of looked like this, like it was going up at a faster rate. I've still drawn something that's rising. It's still going up, so the function is still increasing. However, it's increasing at a slower and slower rate. You see how the position here is kind of topping off, as if my car, although moving forward, is slowing down to approach a stop sign, okay? So this is what we would call concave down. Although f prime is still greater than 0, which is to say that f of x is increasing here. If we took a plot of f prime, although f prime in miles per hour is positive, f prime itself is not increasing. F prime is decreasing like that, okay? You see the difference? In both of these examples, the first derivative that represents the speed is positive, which is to say that my car is moving in the forward direction. However, in the first example, the car was moving faster and faster and faster. So its second derivative was positive, its first derivative was increasing. Now I've got an example here where my car is still moving forward in space and time, but it's doing so at a slower and slower rate. So if I plotted the output of what I would see on my speedometer, you see first I'm going 20 miles per hour, then 10, then 5, then 2, then 1, and now I've hit a stop sign, so now I'm going to go 0 miles per hour, and sure enough my position is just going to top off, which is to say I'm not going anywhere anymore. I'm not increasing my position on the road. Okay, so this is still x in hours. But you can see here on this graph, f prime is decreasing. And I want everybody to understand the difference between a function value being positive or negative versus the function behavior being increasing or decreasing. Okay, so the function value of f prime, the speed, is still greater than 0. However, the rate of change of this function, although the function is still above the x-axis, is that the function's going down. So f prime, although positive, is decreasing, and the conclusion that you can draw from that is that its derivative, or f double prime, the second derivative of position, is less than 0. So in this case, the car is decelerating, it's slowing down to a stop, whereas before it was accelerating, coming up from a stop, going faster and faster. Okay, so that's the difference between concave up and concave down. And now I'm going to show you guys a really cool trick so you can tell always the difference between concave up and concave down versus increasing and decreasing. Okay? This is a really cool trick. I got it from a book called Apex Calculus, which is a free book if you want to look it up on engineering calculus. And here I'm going to call this the 4 combinations of increasing versus decreasing and concave up versus concave down. Now you can see from what I just did here on the board that increasing, decreasing, and concave up, concave down are two completely separate things. Something can be increasing and concave up, and it could be increasing and concave down. Likewise, it could be decreasing and concave up or decreasing and concave down. So one of the choice between these does not imply what's going to happen on the choice between these. Those are separate issues. How can we understand all 4 of these combos together? Let's draw a circle. Okay? And each of the 4 quarters of the circle turns out that it's going to be a different combination of increasing, decreasing, and or concave up and concave down. Okay, so on my last example here, you can see in both cases the function was increasing. So you see that I've separated a circle into 4 quadrants here. Can you pick out which 2 out of these 4 would represent a function that is increasing? Which 2 of these segments here do we have a function that's increasing? Right here, right? The function is going up here, just like this picture over here. And what about this one? No, the function's going down. What about this one? No, function's going down. Over here, the function's also increasing over here. Okay? So this one right here, f is increasing. And this one right here, f is increasing. Okay, so this brings us back to our previous example. In one of these increasing cases, the function is increasing at an increasing rate. It's accelerating, and that's going to be concave up. Can you pick out which one of these is going faster and faster, accelerating? That's this one, right? This is the one that I drew before about the car, where not only is it increasing in its position, but its speed, it's revving up, going faster and faster and faster. So, and F is concave up for that one right there. All right, and so which one's concave down? That's the other one, just like I drew over here, where although the position is increasing in time, it's doing so at a slower and slower rate. Its speed is decreasing, so it's decelerating. Its acceleration is negative, its second derivative is negative, and so F is concave down, which is synonymous with having a negative second derivative. Okay? So you can see that you can be an increasing function and be either concave up or concave down. Now let's take care of the other two segments here. Hopefully you recognize that on both this segment here and this segment here, the function is decreasing. The function is going down. It's lower than it was before. Okay? Which one of these is going to be concave up? Which one of these is concave up? It's decreasing, but the rate at which it's decreasing is increasing. Is that confusing? It is a little bit. All right, so this is the one right here where F is decreasing. Okay, you can see that F is going down, but it's not going down and getting worse and worse and worse. What's happening is it's going down, but it's kind of topping off, so it's kind of leveling off, so it's not so bad. We're going to call that increasing because if you think about the slope of the tangent line, the slope of the tangent line is very negative here. It's very large and negative. But as I move along the function, you see how my arm is getting more and more horizontal? And if you think about the negative value of the slope, that value is getting less and less negative, which is to say that this slope is actually increasing because it's getting less negative. Okay, so this is decreasing, but it's also, F is concave up. All right, because at least it's not getting worse and worse and worse, right? Here's the one where it's decreasing and it's concave down. Because you can see it's decreasing because the function's going down. Not only is the function going down, but it's going down faster and faster and faster. It's really plummeting. Okay, so this is the one that we call concave down because if you think about the slope of the tangent line, first the tangent line is just a little bit negative. Now it's more negative. Now it's more negative. Now it's a really big negative number. So actually the value of F prime is getting more and more negative. F prime is decreasing, and so that's why I say right here, F is decreasing, and as well, F is concave down because the derivative is also decreasing. Okay, so to really make sure that you understand the concept and the comparison between increasing, decreasing, and concave up, concave down, I would invite you to try to draw this four-segmented circle by yourself. Just get out a completely fresh sheet of paper and draw these four segments of the circle and then see if you can recreate this fact that I have right here. It's going to be really valuable for you to understand increasing, decreasing, and concave up, concave down before we get into the applications to business. Okay? Alright, so one more thing I want to say about how you can tell whether something is decreasing, if something's concave up or whether it's concave up or concave down, is you can think about the rain. Does anybody out there think about the rain? If you're taking this class with me in Olympia, Washington, you know it's one of the rainiest places out there. Okay? On a concave down function, that's going to be like your umbrella. Okay? So concave down is like an umbrella. You can see that if I separate it right here, the things that are above this dotted line are concave down, the things that are below the dotted line are concave up. So if you think about the rain starting to rain down, is this function going to protect you from the rain? Is it going to keep your head dry? Well, if the rain's going to come down upon this function right here, you can see it's just going to roll off. It's like an umbrella, and the rain cannot get underneath it. You see, the water does not collect when the rain falls down on a concave down function. And the difference between that and this one, concave up is like a cup. And that actually rhymes, so that can help you to remember it too. Concave up is like a cup. Which is to say that if the rain came down on the concave up function, it would start pooling up and collecting inside here. See, it would be like a cup where it would all collect it. And so what would you rather have if it's raining? Probably something concave down where the water's just going to roll off. And if you're really thirsty, you would want something concave up like a cup because that's what would collect the water right there. Okay, in the next video, I'm going to throw up a function at you, and then I'll ask you which portions of it are concave up and which portions are concave down.